Hello students, welcome back to this lecture series for M.Sc. Part 1 Physics, subject that is mathematical methods in the physics. Okay. In the last lecture we had talked about the simply connected region and the multiply connected region, and also we talk about this harmonic functions and analytical functions. Okay. So what is simply connected region? Simply connected region. So this is one regions we consider, that is we defined with the R, and in this region one suppose point P and one closed loop or closed curve. This is curve. I am giving the name gamma or the C. Okay, so in the simply connected region, this is the region. So when this closed curve is shrunk to the points without leaving these regions, then we call this is a simply connected regions. Okay, and for the multiply connected regions, in the multiply connected regions, here also one this is D. Okay. This is D, or you can call this is regions, domain or the regions. It is the same things. Okay. So when suppose I consider the one closed loop in that region, it is C curve, and here is a point. So this curve when shrunk to the points with the leaving these regions, then we call this is the multiply connected regions. Okay, so this is the difference between the simply connected and the multiply connected regions. So that what we discussed in the last lectures. Okay, so today we are going to discuss one important theorem, that is a quasigorset theorems. Okay, and before that I would like to introduce f of z, that is path dependent, or if it is path dependent, then we call this f of z is not analytic function. Okay, so when it is path dependent, then this f of z is not analytical functions. Okay, or when this f of z is path independent, then this f of z is analytical functions. Okay, so this is different. So now point is by the Cauchy integral theorems, we can discuss about this multiply Cauchy integral theorems. We discuss for the simply connected region and the multiply connected regions. Okay, so first I am discuss for the simply connected regions. So when f of z is analytical, Goursat theorem. Okay, so when f of z is closed integral over the curve, this is for the closed curve. Okay, so these expressions, these closed integrals, we can write when suppose this is planes, and in that one we consider the closed curve. So for this is a point A, this is a point B. So when we starting from the point B, and again again I am reaching the point, same point B. Okay, so for this we can write, for this when we integral over the closed curve, so we can write this expression, closed integral over C. Okay, this is a curve. So this closed integral is equal to 0, okay, when we reach to the same points of the integrals, okay. So closed curve C into f of z, or sorry here dz is equal to 0. So this is what we are going to prove for the simply connected region, okay. This is expressions. So f of z, that is a you already in this f of z is continuous and analytical functions. This is analytic and continuous functions, and f prime z is continuous in the domain or regions, okay. Here I am considering the domain D, okay. So this f prime z and f of z is a analytical functions, and this f prime z is a continuous in the domains D, okay. So then we can call this a closed integral C f of z dz is equal to 0, okay. So for this is a closed curve, so we know the f of z is, we can write this f of z, this is a functions, we can write u into x y, u is a function of x and y, plus iota into v x and y. So this is expression for the functions, and if we write for the dz, so dz is like z is a x plus iota into y, z is equal to x plus iota into y, and if we write dz, so this is equal to dx plus iota into dy, okay. So here we can rewrite this f of z dz in the term of this u, v and dz, okay. So if close C f of z dz, okay, our task is what, these expressions we want to show this is equal to 0, okay, close for the closed loop or the closed curve, okay. So this close integral C f of z dz is equal to, we can write this expression, that is close C u plus iota into v into dx plus iota into dy, okay. So we know that if we simplify, then close C, we can write u dx minus v dy, okay, plus iota into close C, this is v dx minus u dy, okay. Okay, so this is expressions for this f of z dz, closed integral C f of z dz, okay, when we putting this f of z is equal to in the term of the u and v. So now we know the Green theorem, okay. This is from line to surface integral. So if phi and psi, these are the continuous functions, then we can write this phi and psi is a continuous differential functions, okay. So for that by using the for the Green theorem statement, like or the expression for the mathematical expression for the Green theorems, if we write, so this is equal to same things, it is close so it is close phi dx plus psi dy is equal to, okay, this is a closed integral ratings, and double integration over r, this r for the regions, so it is equal to dou psi by dou x minus dou phi by dou y dx into dy. Okay, so this is a line integral into the surface integral. This is a surface integral dx into dy. Okay, two coordinates variables. So if this u and this phi and psi is satisfy the continuous differentiable condition, so if this u and v, this also the satisfy the same condition, so we can write this expression for this terms u and v. Okay, because this u is a differentiable functions in the region R, and this phi and also this is a differential functions in the region R or the domains. Okay, so this u and we also satisfy these conditions, differentiable conditions. So we can write suppose for this term, if I write, then u is a phi, and v is a psi. Okay, so for only this first term, first brackets, okay, so it is equal to integral, double integral or r into dou psi is what v, so here is a minus v. Okay, so here psi is what dou psi by dou x, so here is a minus v. So for that I am writing here the minus dou v by dou x minus now dou phi, okay, this dou phi by dou y, so this is phi we can write for the u. Okay, into dx by dy. Now plus another terms is here, that is I turn to close integral c v dx minus u dy. Okay, so I turn to double integral over r. Okay, now this u, this can be changed as, now here v dx minus u dy. Okay, so v is now psi, sorry, v is now phi, and the u is now psi. Okay, so here just write for u is now psi, so it is dou u minus and dou x minus dou v by dou y dx into dy. Okay, this is the expressions for by using the green theorems. This is expression for close f of z dz over the c. Okay, so let me check. Okay, right. Now if this u and v satisfy the differential or it is, if it is by the CR equations, we know that this v of x we can write by CRx first order of derivatives that is equal to 0 if we take this two terms dou v by dou x minus dou v by dou v, so this is equal to 0. Okay, so by CR equations or the CR conditions we can write two conditions, that is ux is equal to by CR Cauchy condition. Okay, so ux is equal to v of vy and vx is equal to minus vy. Okay, so this is equal to dou, we can write dou u by dou x is equal to dou v by dou y. Okay, so this we can write as dou u dou x minus dou v by dou y is equal to 0. Okay, and for this this is dou v by dou x minus, sorry, is equal to minus dou u by dou y. Okay, so this we can write minus dou u by dou y so this is minus dou u by dou y, and it is minus dou v by dou x is equal to 0. Okay, so from this we can write dou u by dou x, okay, minus dou u by dou y is equal to 0, and minus dou u by dou y minus dou u by dou x. Okay, so it is equal to 0. So if you observe these equations, dou u by dou x minus dou u by dou y, so this is this terms, okay, that is equal to 0, and minus dou v, actually here is a mistake, this is x y, right? So okay, right, so minus dou u by dou y, we can rewrite these terms as, okay, this is, we can rewrite as minus dou v by dou x minus dou u by dou y, for your understanding. Okay, so this minus dou v by dou x minus dou u by dou y, this is these things. Okay, so this is equal to 0. So what is our task by this Cauchy-Goursat theorems? This closed integral c or c f of z dz is equal to 0. If you put this 0 and 0 in this term, so it is equal to closed integral over c f of z dz is equal to double integral r, this is 0 dx into dy plus at into double integration over r 0 dx into dy. Okay, so this is equal to 0. So we can write closed integral f of z dz is equal to 0. Okay, that theorems is for the this is for the simply connected region. Okay, now if this we can apply for only the simply connected regions, these theorems we can apply for the only simply connected regions. But if you want to apply these conditions or this theorem for the multiply connected regions, that then what the procedure to apply this theorems. Okay, so let's check this procedure to check for the multiply connected regions. Okay, so now f of z dz is equal to 0. Okay, so this is Cauchy-Goursat theorems. We are now apply for the multiply connected regions. Okay, so for multiply connected regions, so first task is what was, suppose here is a multiply connected regions, that is, okay, this is a multiply connected regions, it is C1 and okay, this is C2, and this is a domain D, Y and X. So this is multiply connected regions, doubly connected, it is doubly connected. Okay, so this is a curve this is the regions that is between this C1 and the C2. So here if I draw the closed loop, and then it is sum to the point suppose point P here, and it is shrunk to the point P with leaving this regions or D, then we can call this is a multiply connected regions. Okay. So this is is a doubly connected region. So for the doubly connected regions, I am consider now procedure is what, to make this doubly connected to the simply connected regions. Okay, so this is doubly connected region. Okay, now first task is what, is just make this, it is a simply connected region. So for this just I am make a cut, small cut to the or make one line over the regions, so we can make this simply connected regions. Okay, so procedure is what, suppose this is a doubly, same things. Okay, it is a doubly connected regions C2 and this is C1. Okay, so just I am making a cut here, that is P and this P and Q. This is the important things. Okay, when we study this conversion of the multiply to the multiple connected to region to the simply connected regions. Okay, so just I make here the cut. Okay, so this cut make a passage between this point P to Q. Okay, like this. So just this point is P, this point is P, and this is also P, because this passage is very small. Okay, as only we just cut. So this P is what, this point P and this point is the same things. Okay, for your understanding I am draw like this. So this point is same, this point is also same, and its direction is, so this is like this. Okay, so this is C1, sorry, C2, and this is C1. So P, this is suppose S point, R, and this is T. Okay, so this is now the simply connected regions. So procedure is what, just make a small cut over here, so you can here just passage you can create here, and then this is just simply connected region. So we from doubly connected region to make this simply, this is now simply connected regions. Okay, so similarly way you can if you can apply for the triple connected or triply connected regions. So there you cut two cuts you can do, and you can get simply connected regions. Okay, so now these conditions, close C f of z dz, if we apply to this, so here is from, if we starting from point P, R, S, P, Q, T, P. Okay, so this is one integral, or from when starting from one point and again we reach to the same point like this. Okay, so if I write closed integral over P from here, P, R, S, P, Q, T, okay, Q, T, again Q and P. Okay, so this is way when we are completing the path of this closed loop. Okay, so this f of z dz, when we integral or this loop, then we get a 0. Okay, so that let's check first here. So from the P, S and P, this is now this divide into the parts. Okay, this is one C1, that is one part, this is a second part, this is a third, and this is a fourth part. Okay, so close C, that is P S P. Okay, sorry, P R S P. This is the first one, that is f of z dz is equal to this is the first one, and plus close integral, that is P to Q. Okay, so it is PQ f of z dz, and third one, that is plus close integral, that is Q T and Q, Q T and Q f of z dz, plus now last one, that is integral over these lines, that is a Q to P, Q to P, that is f of z dz. Okay, now if you observe this 2P to Q and Q to P, so this is the opposite things. Okay, directions, this is in the positive, suppose this is x direction, so it is a positive x, and this is a negative x. Okay, so this we can cancel P to Q and Q to P. This is P to Q and Q to P. Okay, so this we can cancel. Okay, if we write is integral over PQ, so here integral over PQ, so here is a minus signs. Okay, so these two terms we can cancel from this. Okay. Now remaining terms, close C f of z dz is equal to close P R S P f of z dz plus second term, that is close integral Q T Q f of z dz. Okay, so this is this first expression for this C1. Okay, and the second this expression for this C2. Okay, close loop. So this is if I write like this, in this way, for this close integrals, here is the directions. This is a closed integral, and here is the directions, that is f of z dz. Okay, that is P R S P is equal to close, so these directions and this closed integral, this direction is opposite. Okay, so this is we can write f of z dz q t q. Okay, so if we write these things like this, if you write like this, so here is a minus sign. Okay, so we can write these two things is the same, but on the same things. Okay, so there also direction is changed. So this is, if this is equal, so this f of z expressions we can write this is equal to 0. P R S P. So we can write C f of z, or okay. This is for the multiply connected regions. Okay, so close P R S P Q T Q P, this closed loop, if take the integral over this closed loop, so the f of z dz is equal to 0. Okay, so this is about the doubly connected regions. So when we discuss about suppose when we discuss for the triply connected regions, so there we make two cuts. Okay, so for the triply connected regions, so in the triply connected region there are two this is C1, this is C2, and this is C3. Okay, so here we can make the two cuts, one here and another here. Okay, so this is like if we make a cut here, so this like this, and here is also. Now you can observe this region is a simply connected regions. Okay, for the triply connected, if we make a cut here, okay. So also we can apply these things to this triply connected regions. Okay, so like this we can first make this multiply connected region to the simply connected regions. Okay, so let's stop here. We will discuss in the next lecture. Okay, thank you.